Welcome back to 9.4. We're still dealing with sets and probabilities, but in 9.4, we're talking about binomial probability. And the prefix bi means two. So that means that we're talking about probabilities where there are only two outcomes. So this is based on the idea of a success or a failure. Those are our two outcomes. It was created by Jacob Bernoulli. They're called Bernoulli trials. And there are 4 requirements that have to happen for this to be a true binomial experiment. So the same experiment has to be repeated a fixed number of n times. So if I were to say, I'm going to flip a coin until I get a heads, that is not a fixed number of times because it could be different for every person. Number 2, there are only 2 possible outcomes, success or failure. Number 3, the probability of success for each trial is independent. And number 4, the repeated trials are independent of one another. So if you are dealing out a deck of cards, and as long as you replace the card back in before you take another card, then that's considered independent. If you don't have replacement with your experiment, then it's dependent. And then X is going to be any outcome of 0 to n, where n is the number of trials. So let's look at our first example. It says, a trainer is teaching the dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%. The trainer attempts the trick with the dolphin 20 times and counts the number of successful tricks. Explain how this meets the 4 requirements of a binomial experiment. And I'd like you to show n, p, q, and x. So number 1, n is equal to 20. We're going to do the experiment 20 times. Number 2, success is a completed trick, and failure is the whale did not do it. The dolphin did not do the trick. Number 3 is the probability of success is 35%, and the probability of failure, we also call that Q, is 1 minus 0.35 because they are complement, success and failure. They add to 1, which is 0.65. And yes, each time they do the attempt to do the trick, it's independent. Now, some might say it's dependent because the dolphin may get tired after so many attempts, but we're going to treat this as independent trials. X is the number of successful tricks. And X can be anywhere from 0 successful tricks all the way through all 20 attempts were successful. So a binomial probability is defined if P is the probability of success in a single trial of a binomial experiment, the probability of X successes and n minus X failures in n independent repeated trials of the experiment is found such as this. So we're going to use a combination of n choosing X times the probability of success to the X exponent times 1 minus the probability of success to the n minus X exponent. And we're going to learn this mainly in chapter 10, but it's never too early to start talking about what would be considered an unusual probability. I mentioned it in 9.3, but an unusual probability if the probability is less than 5% or 0.05. So it's something to keep in mind as we're working along. Let's look at example 2. It says a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs a trick is 35%. Again, out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the probability question mathematically. So that would be the probability that X equals 12, exactly 12 times. So that would be 20 choosing 12. Success is 0.35 to the X, which is 12. 1 minus 0.35 to the X minus, to the N minus X, which is 8. 20 minus 12. So we can put this into Desmos. And the link to the Desmos work is in Canvas. So there you can see at the top, we have 20 choosing 12, 0.35 to the 12, 1 minus 0.35 to the 20 minus 12. So that likelihood is 0.0136. Let's look at the next example. We'll come back to this binomial stuff in a minute. So example 3 says, a pair of 6-sided die is rolled 10 times. Each roll is independent. You want to find the probability of rolling a 1, 5 of the 10 rolls. So we have to identify n. N is 10. We're going to roll the die 10 times. And a success is rolling a 1, and that can happen as 1 over 6 because there's 6 sides to the die. That means Q, or the probability of failure, is 1 minus P, or 1 minus 1/6, or 5/6. So the probability of getting 5 of the 10 rolls, so probability of x equal to 5, is similar to example 2, 10 choosing 5, 1/6 to the 5th, 5/6 to the 10 minus 5, and that comes out to be 0.013. Again, you can see this in Desmos. But now example 4 is a little bit different. We're again rolling a fair 6-sided die 10 times. Each roll is independent. This time you want to find the probability of rolling a 1 less than 3 times. So less than 3 times means that we could have possible outcomes of 1 time, 2 times, or 0 times. It has to be strictly less than 3. Pardon me. So that's the probability of x being less than 3. So that means we can find the probability of x equal to 0 and add it to the probability of x equal to 1 and add that to the probability of x equal to 2 because it's OR. Any of these will satisfy less than 3. So you can see that I did these in Desmos, in the Desmos link. So this is there is 0 of them, there is 1 of them, 0.323, and there is 2 of them. And then we're going to add those together, and that probability is 0.7752. Okay, let's go back to our paper here, our notes. So the next example says, according to a study conducted by the American Veterinary Association in 2006, 37% of American households had a pet dog. If a sample of 10 random households is conducted, what is the probability that at least one household will have a dog? So X is the number of households that have a dog. That's what we're counting. The probability of success is 0.37. And we want to know the probability of at least one. So if we go back to what we've learned about the at least one, we can use the complement of 1 minus the probability of no dogs. That will make it easier. because otherwise, at least one, we would have to go through all 10 households and go 1 plus 2 plus 3 plus 4 plus 5 all the way through 10. So instead, we can just subtract the one that we don't want, which is the probability of none of the households having dogs. So we're going to find the probability of none of them having dogs and subtract that from 1. And that is 1 minus 0.0098. And that is 0.9902. And again, you can see that in decimals. Okay, so let's go to the next example. The next example says, it has been stated that about 41% of adult workers have a high school diploma, but did not pursue any further education. If 10 adult workers are randomly selected, find the probability that at least 6 of them have a high school diploma, but do not pursue any further education. So this is a unique situation because at most 6 means that I am looking for anything up through 6. So x less than or equal to 6. So I would include 0, 1, 2, 3, 4, 5, and 6 and add them. And using a complement, I would go 7, 8, 9, and 10 and add them. So using a complement doesn't really help too much. So we're going to use Desmos to shorten what we're doing with these combinations. So instead of doing the combination out like we had in examples 1 through 5, we're going to use a new command in Desmos. And that is called the Binomial Dist. So you do need to know your n, which is 10, and your probability of success, which is 0.41. And so you're going to type Binomial Dist, parentheses, 10, comma, 0.41, n, comma, p. And because it's less than or equal to 6, it's a group of outcomes that satisfy this probability. We're going to check the box that says find cumulative probability. Our minimum will be 0 and our max will be 6. And so that probability is 0.9374. And you can see in Desmos that it creates a distribution and it draws a line and colors in the circle solid the ones that are included in the probability that we chose. So in the notes, some of you may have updated notes. In these updated notes, I have added a little table for this to help with some of the wording. So if you are looking for an exact equal to outcome, the phrase down here in the table might be exactly or equals or is, none, all, or a given number. And we're going to use the equal sign as our math symbol. Then you do not need to check the cumulative box, and you don't have to worry about the min or the max. You're just going to follow the suggestion up here under click on the magnifying glass to adjust the shape of the graph, and then find the probability with the associated value because it's a single probability. The one we just did in the notes is a group of outcomes. And so we're in the bottom 3 situations. So we were in the at most, which is right here, less than or equal to, not more than or at most. So our symbol is less than or equal to, Yes, we're going to check the cumulative box, and that means the min is going to be 0 and the max will be our x, which was 6. So we're going to use this throughout the notes, throughout the rest of this lesson. So the next part, letter B, says, how many adult workers out of 10 do you expect to have a high school diploma, but do not pursue any further education? So expected value for a binomial situation is given here in the box. The expected value for the binomial probability is found by taking just n times p. So if we do n times p, that would be 10 times 0.41 or 4.1 students, adult workers. So the description that we would give is out of 10 adult workers, we would expect on average 4.1 of them to have a high school diploma, but do not pursue any further education. Let's look at example 5. Example 7. Example 7 says approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a statistics class of 50 students, what is the probability that at most 40 will do their homework on time? Students are selected randomly. So at most is going to be less than or equal to 40. And this is what it should look like in Desmos. And I've attached the Desmos link so you can go through there. So the box will be checked and it's 50 and the P is 0.7, min is 0, and max is 40. And that probability is 0.9598. B says, in a statistics class of 50, what is the probability that at least 30? So you probably have the updated notes. At least 30 will do their homework on time. So at least 30 means it's a greater than or equal to symbol. And we're checking the cumulative box. And it's greater than or equal to, so X is now the minimum. And max is going to be our N, which is 50. And that probability is 0.9522. And then letter C says, out of a class of 50, what is the expected number of statistics students to do their homework in time for it to be collected and graded? So that would be N times P, or 50 multiplied by 0.7, which is 35. And we would explain that as out of 50 students, we would expect 35 of them to turn in their homework on time. Always reference out of N, because N directly affects your expected value. So if it's out of a different number, N, we would have a different expected value. So that's important to reference that. So in the numbers section of Time magazine, it was reported that 15.2% of low birth weight babies graduate from high school by age 19. It was also reported that 57.5% of their normal birth weight siblings graduated from high school by 19. They're siblings, which is interesting, and it's definitely a higher percentage. So if 40 low birth weight babies are tracked through high school, what is the probability that fewer than 15 will graduate from high school by age 19? So there's our N. Our probability of success is 0.152 for the low birth weight babies. And we're doing fewer than, which is a strictly less than. So this time, it's a strictly less than. So our min is 0, and our max is X minus 1. Because we're not including 15. And B says, what are some of the factors that may contribute to the wide difference in high school success between these siblings? Do you believe that low birth weight is the primary cause of the difference? What other information do you need to better answer these questions? And a few things that we could throw out are babies that have low birth weight will probably have later brain development. They may have lower immunity. And we don't know the economic income or if it was a single or two-parent family. So we said there were some other social variables that could come into play here. Example 9. DNA evidence has become an integral part of many court cases. When DNA is extracted from cells and body fluids, genetic information is represented by bands of information, which look similar to barcode at a grocery store. It is generally accepted that in unrelated people, the probability of a particular band matching is 1 in 4. So the probability that two bands match is 1 in 4 because you would obviously match to yourself in unrelated people. So that means the probability that two bands match in related people would be 3 out of 4. If 5 bands are compared in unrelated people, what is the probability that all 5 of the bands match? And so that would be n equals 5. Probability of success is 1/4. And we're checking for probability of x equals 5.001. Not likely. If 20 bands are compared in unrelated people, what is the probability that all 20 of the bands match? And if you put this into decimals, it comes out to be almost 0. So that's what it's going to show as 0 when you look at the distribution. So if you were deciding on the child's paternity and there were 16 matches out of 20 bands compared, would you believe that the person being tested was the father? So the likelihood of unrelated, if they were unrelated, matching is virtually 0, but they actually did match. We would definitely say that it's most likely that it is definitely the father, because it's very unlikely that this would randomly happen. Catch me back for more videos.